So there's two kinds of TI-84s. There's the new ones. They're actually, the price has gone down. It's the TI-84 plus CE. If you're going to get a graphing calculator, that's the one to get. I kind of encourage you to do that if you're planning to go on in math. You're going to take the SATs, things like that. This is the calculator you can use. It does give you an advantage. Getting it soon will allow me to teach you how to use it. I'm going to record. I record everything, as you know, and so all the recordings will still be up here. Even if you get it in the future, you can go back and look at any of the recordings on how to do stuff on the TI-84. I'm going to show you how to do piecewise functions now. So with piecewise functions on the new one, you would start off in, here's what it looks like when you're just in the home screen. When we want to graph something, we go y equals, and then I want to build a piecewise function there for y1. Well, here's how I do it. If I go to the math menu, and then if I go clear down that math drop down, there's a bunch of different drop down menus in the math screen. And I'm just going to use the first one. But rather than going down a whole bunch, I'm just going to hit the up arrow to circle around to the bottom of the list. And if I hit the up arrow twice, look where I end up on piecewise. So if I hit enter, it allows me to choose the number of pieces by using the left or right arrow. So if I go to the left, it gives me fewer pieces. To the right, it gives me more pieces. I want 3 pieces. So I'll go down and hit OK, enter, and it builds me that template. Look how easy that is. Exactly the way it looks on paper is how it looks on the new TI-84s. So I'm just going to fill in all those little blanks in the template then. So the top one, I need the function and the domain. The function is 2x, and look where the x's are. The x's, there's a key for x. There's a built-in key for the variable, just to the right of the alpha key. So there's my 2x. I'll hit the right arrow to scoot over to the right to the domain part. I'm going to fill in the domain. X is less than or equal to -2. So I need an x, and then I'll go second math, gets me to the test menu. And there's all my different inequality symbols. So I'm going to use 6 less than or equal to, and then I just need a negative. There's the negative sign, -2. I'll scoot down to the middle function, which has the equation. I need to do a -1 minus x. That's my negative sign. That's my subtraction key, right? So I'm going to go -1 minus x. There's the function. I'll scoot over to the right for the domain. Now, one really nice thing about the new newer version of the TI-84 is when I have a compound inequality, I can enter it exactly the way it looks. You didn't used to be able to do that. On the older ones, you can't do it that way. So I can just go -2. I need a less than symbol. So I go second math 5. Is the option for a less than. I need an x. I need another less than, so I go second math 5, and then I need a 4. Okay, now I go down to the last piece. Well, the equation or the rule for the last piece is -3. The domain is x is greater than or equal to 4. I'll even show you one more little shortcut here. If this isn't a big deal, you don't have to do this, but if you go down to the second and you go to the math screen, if I go over to the conditions menu, it's already got like x is less than or equal to, less than, greater than. It's already got all that stuff built in, so it saves you maybe just like one keystroke. So I can do x is greater than or equal to, and then put a 4. And now I want to graph it. But to graph it, I don't just hit graph. I want to always reset the screen so it's going from, it's reset to its normal settings, where the x-axis is going to extend from -10 to +10, and the y-axis goes from -10 to +10. And I do that by just hitting the zoom menu and then 6, zoom standard. So instead of graph, you always just hit zoom 6. And there it is. There's my piecewise function. Okay. Now, how do I know where the endpoints are? Right? Well, they don't show up on the graphing calculator, and that's one of the downsides of using graphing technology to graph piecewise functions. We don't know which endpoints are closed and which are open. There's an easy way to find out, though. If I ever want to evaluate anything, any function that I've graphed, there's a shortcut for that. Technically, the way you do it is you use the calc menu. That's the menu for doing stuff with graphs. If I go second, calc, and then I can do all kinds of things. I can find the zeros of functions, the x-intercepts. I can locate the minimum and a maximum of the function if I want to. I can find where graphs intersect. I can find the slopes of graphs, all kinds of stuff. Well, the first one is value. If I choose value, it's going to ask me for an x value, and I can plug in any value I want to. Like, what if I plug in 0 for x? Then it tells me, when I hit enter, it tells me that when x is 0, y is -1, and it shows me where that point is on my function. There it is. It's 0, -1. It's on that second piece, isn't it? Okay, well, I could do the same thing, but what if I evaluate the function at the boundary values of x, which are -2 and 4, right? There's a shortcut for this. Rather than having to go through that whole menu, I can just use trace. If I just push the trace button and I type an x value, like what about -2? And then I hit enter, it automatically jumps me down to that part of the graph. Well, when x is -2, y is -4, and look where it puts me. It puts me at the end point of my first piece, right? The top piece, which makes sense because -2 is included in the domain of the top piece and not the middle piece, right? If I want to know where the other endpoint is, I could do the same thing. I could just go trace 4, enter, and I know that when x equals 4, y is -3, and it puts me, the closed endpoint is on the bottom piece, which I can see because that's the piece that includes 4 in the domain. Okay, everybody see that? Okay, simple. It's just it's just what you'd expect. It's very straightforward and simple on the new TI-84s. Okay, here's a screenshot of what the graph looks like, what the y equals menu looks like, and more importantly, here's a key press history, right? So if you want to do what I did, starting from the home screen, this tells you exactly what buttons to push, and that 2 means you just push it twice. Okay, you push the up arrow twice there, but that's exactly the history of the buttons that I pushed right there. Okay, what about on the other calculators? Okay, so let's switch over to one of the older ones. Okay. Oh man, that converts it. That's pretty cool. Huh. Anyway, well, let's build it from scratch. Okay, so if I want to build a piecewise function on any of the other TI-84s, they all work the same. It's a little bit harder to do, but it's not terrible. So this time you have to kind of input the section, sort of like we did on Desmos. So we're going to input the domain first for the first piece, and we have to put it in parentheses. So in parentheses, I would do x is less than or equal to -2. You do that the same way. So second math 6 is less than or equal to -2. Close the parentheses. So there's my domain. And then right next to that, so it almost looks like you're multiplying them. You're not really multiplying them, though. In parentheses, you're going to put the function. What's the rule? Well, the rule is 2x. Okay, there it is. So there's the first piece of my piecewise function. Okay. When I want to add the other pieces, I'm just going to add them. So I'm going to do plus, and now I'm going to do the middle piece. I have to put the domain in first. So in parentheses, I've got to do this domain. Okay, the downside, the big downside here is that you can't put a compound inequality in the way that it looks on any of the older TI-84s. You have to use the word and if it's a compound inequality like this. So think how we would say this. We would say this: x is greater than or equal to -2 and x is less than 4, right? So that's how we have to input it. I'll do x is greater than -2. So second math 3 is greater than -2. And now I need to get the word and, right? Where does and come in? Well, that's on that same screen. If I go to the test screen, the one that's behind math. So second math gets me to the test screen. If I scoot over to the right to the logic menu, then I've got and, or, not, all kinds of logical things that you'd use like in programming or something. But there's the word and. So I'm going to hit enter for my and. And the other part of that compound inequality is x is less than 4. So I'd go x is less than 4 and close the parentheses. Now I need to put in the function there, right? I put in the domain. So now in parentheses, I would just put -1 minus x in parentheses. And then I'm going to do a plus sign. So I'm going to add the last piece of the function. The domain is x is greater than or equal to 4. So second math, option 4 is greater than or equal to. So I hit 4, number 4, close the parentheses. And then right next to that in parentheses, I need to put the equation or the rule, which is just -3. Close the parentheses. Now if I hit zoom 6, I get the same graph. It just takes a little longer to do, but you get the same result. And the trace feature works exactly the same way. So I can test the endpoints just like I did with the new TI-84. Okay? All right, so there it is. That may or may not be something that was hugely fascinating to you, but if you end up getting a TI-84, if you don't already have one, just access this video and you'll be able to remind yourself how to do that stuff. Okay, and once again, here are for the other TI-84s, here's a keystroke history, the keys that I pressed, okay, for all the other ones. All right, so last issue we want to go through today. We want to take a look at, okay, and we did a little bit on this yesterday, didn't we, right, or the other day. We talked about greatest integer functions, and we talked about the beads, and we kind of got an idea. This is what the graph of a greatest integer or a floor function. They mean the same thing, right? Sometimes we call them floor functions. I prefer to call it a floor function. Greatest integer function is too hard to say. In programming, typically it'll be a floor function. That's what they'll call it. On Desmos, they call it a floor function. So let's call it that for now. So here's the graph of our floor function. Okay, it makes sense, doesn't it? Because think what that was doing, right? What did our floor function do? Remember what it did from the other day. When we input a value of x, right, we input a value, the output that the floor function calculates is the greatest integer less than or equal to the input x, whatever value we input. So if I input a 7, the greatest integer less than or equal to 7 is 7. If I input a 2.3, the greatest integer less than or equal to 2.3 is 2. If I enter a -4.8, the greatest integer that's less than or equal to -4.8 is -5. And just like we said the other day, imagine that you're just sliding a bead to the left until it hits, there are knots at all of the integers on your number line. You're just going to slide the bead along that string to the left until it hits a knot. That's how you can kind of think about that process. If we're doing a more difficult function where we've got we're doing some other stuff inside the floor function, just remember that the floor function doesn't care how it gets the numbers. You're just feeding it numbers and it's generating outputs, right? So for example, let's look at this middle example here, f of 0.5, right? If my floor function, this is my floor function, it's right here, right? The floor of x minus 5. That's where I'm plugging in my value of x. So if I'm going to evaluate this at 0.5, then that x is turning into a 0.5. And now I'm taking the floor of 0.5 minus 5. Well, I've got to turn that into a number that I can feed the function, right? 0.5 minus 5 is 4.5. And the floor of 4.5 is just 4, right? The greatest integer less than or equal to 4.5 is 4. So we might have to do a little bit of calculation to simplify the number that's inside. But once I simplify the number inside the floor function, then I feed that to the floor function and it spits out an integer, right? Okay, this makes sense in terms of our graph because if we're graphing, the inputs are my x's and the outputs are my y's. If I start at 0, all of the decimals that I'm feeding that floor function are going to get pushed back to the integer 0 until I get to 1. And as soon as I get to x equals 1, now all of a sudden it spits out an output y value of 1. And it just keeps doing that same pattern as we talked about a couple days ago. And so I just get this infinite step function. It's like an infinite staircase where the closed endpoints of each step are on the left and the open ones are on the right. Okay? All right, give me a 1 to 5 on that real quick. On the floor function or the greatest integer function, what the graph looks like, how we calculate them. Takes a little practice. You're not going to, honestly, this isn't as big a deal as piecewise functions. And so I think I only gave you like 1 or 2 problems on the assignment about that. But I do want to make sure you see this. Okay, and there's what it looks like on Desmos, right? Look how I graphed that. F of x equals floor of x. Okay, let's look at maybe a little bit more complicated example. Let's make a t-table and let's create a graph of this floor function. Okay, so we got the floor of 1/2 x plus 4. Let's fill in our t-table until we can get the trend here. How about? So how about if we do something like let's start at -4. And here's the function that we're plugging stuff into, right? If I'm plugging in an x value of -4, let's do some math in our heads here. We'll do a little calculation. What's 1/2 times -4? Everybody type it in chat. 1/2 times -4 is what? Type it in chat. Good, -2. Okay, plus 4 would be 2, right? So I'm doing the floor of 2. That's what I'm calculating here. What's the floor of 2 going to give me for my y value? Type it in chat. What's the floor of 2? Everybody answer, please. What's the floor of 2? What's the greatest integer less than or equal to 2? It's 2, isn't it? Yeah, so we get 2. So I've got the point -4, +2. I'll put a point right there. Okay, let's try -3. If I plug a -3 in, 1/2 times -3, would you guys agree that's -1.5, -1.5? -1.5 plus 4 is 2.5, right? So I'm taking the floor of 2.5. The floor of 2.5, well, that's 2, right? I slide the bead back to 2. So if I have the ordered pair, x is -3, y is 2. There's another point. Okay. Well, if I pick, what if I pick the value, how about if I pick the value -2.1? Okay, if I have -2.1, 1/2 of -2.1 is negative. I'll tell you what, we'll do that. 1/2 of -2.1 is -1.05. -1.05 plus 4 is positive 2.95. The floor of 2.95 is 2, right? 2 point anything, if I put that into the floor function, is giving me back 2. So if I go just to the left of -2, I'm still right there. But what happens when I input a -2? 1/2 times -2 is -1, plus 4 is 3. The floor of 3 is 3, right? So when I actually go to -2, I jump up to a y value of 3, right? So if I wanted to kind of think about that in terms of filling in the spaces here, that would go all the way over and I'd have an open endpoint there on that stair, wouldn't I? And that jump up to the next one. Well, what's going to happen? I mean, if I keep going forward with this, if I put in -1, 1/2 times -1 is -1/2 plus 4 is 3.5. The floor of 3.5 is 3, so I'm still there. But when I get to 0, 1/2 times 0 is 0 plus 4. I jump up, don't I? I get the floor of 4, which is 4. So I jump up again. So we can see the pattern here, can't we? It just goes like this. Right? We're just going to follow that pattern forever. Okay, everybody see that? How we got that? Just filling in the blanks. Okay, we can do this. Oh, before we go any further, let's write the domain and the range of this. I think that's an important thing. We need some continued practice with that, the domain. So the domain is the set of all the x values in our infinite stair step, right? Are there any x values that are skipped? Think about it in terms of our ant. If an ant is walking along this function, is there ever a place, a value of x, where the ant cannot stand? Or can he stand on every value of x somewhere on the function? Which one is it? So in chat, answer this question. Is there ever a place where the ant cannot stand? See, 2 people have answered. No, he's always got a place to stand, doesn't he? So what's the domain? What's the domain of this whole function then? Yeah, it's all real numbers, isn't it? There's no number that's not included. Every x value, there is no x coordinate that is excluded from this thing. Every x value an ant could step on. If we think about that in terms of projection, right? If I project this function onto the x-axis, we could just project it one step at a time. Give me a 1 to 5 on the concept of projecting a function onto the x-axis. 5 means I get exactly what that means. 1 means I have no idea what that means. If I ask you to tell me, like, what's the projection of that function onto the x-axis, does that make sense? 1, no, 5, yes, or somewhere in between. Okay, I'm definitely okay. It's for some maybe, but I still think there's some questions out there on that. Can somebody ask me a question like what about the projection doesn't make sense, or is it just the whole thing? If I'm projecting something onto the x-axis, think what happens when you project a movie onto the screen, right? You're just transferring the movie onto the screen. It's the same thing we're doing when we project a function onto the x-axis. It's like I'm casting a shadow. If I've got light rays coming straight down from above, what is the shadow that we're casting on the x-axis from this function? And that's the projection. It's like we're taking each of the points and we're keeping their x coordinates the same, but we're squeezing them vertically onto the x-axis. So they can't move side to side. Like this point right here, for example, that little point right there, it's going to have to go straight. I want to do this in orange because remember our domains were in orange. So it's going to get pushed straight down and end up right there, right? That's the shadow that one little piece of the function casts when I shine a light from above. Everybody see that? So if I take this top step, look what happens. I've got this solid endpoint right here on that top step. The projection of that onto the x-axis, and really all I'm doing with the projection is I'm graphing x values, graphing the domain. That's going to give me a solid endpoint, isn't it? And this one right here is going to give me, I'm going to project that open endpoint there down onto the x-axis. So there's my open endpoint. And all of the infinite points in between, in the middle of the stair, are going to get projected down and just fill in the gap in between those endpoints, right? So would everybody agree that the orange graph down here is just a graph of the x values of the blue step? Everybody see that? Give me a 1 to 5 on that concept. Okay, so maybe that's helping a little bit. Okay, good. And if I do that for all the steps, like what if I do that for this step right here? Well, I've got a closed endpoint at that end. I've got an open endpoint over here at this end, and I'm filling in everything in between, right? Well, now let's do this step. Well, that's going to fill, look at that closed end point is going to fill in that open end point, and then it's just going to go, see what I'm saying? They all overlap, don't they? So all of these individual steps are going to end up, when I project all of those infinite steps down onto the x-axis, there's going to be another one up there that's going to fill in that gap. I end up shading in the entire x-axis, so the graph of the domain is everything on the x-axis. It's all reals, okay? What about the range? So yeah, Devin, you're right. It just ends up making a line. What about the range? What's going to happen? Let's take that top step. If I project that onto the y-axis, so I'm only graphing the y values of all of those points on the top step, what's going to happen? Right? Well, if I take that point, that same point I used before right there, if I'm shining a light horizontally to cast a shadow on the y-axis, does everybody agree that's just going to give me a point right there? But don't all the points on that step end up projecting to the same point on the y-axis, right? If I squeeze them all over onto the y-axis, this one does the same thing, that open endpoint does the same thing, but I know that gives me an open endpoint, but look, all these other infinite points fill in that point, right? So does everybody see there that if I project that onto the y-axis, I just get that one point because every point on that step has the same y value? Give me 1 to 5 on that. Okay, so if I did that for all of the infinite steps, look what's going to happen. I'm going to end up just getting that entire step just projects over to that integer value. That entire step just projects over to that point. That entire step projects over to that one. That projects over to that one, and so on. We don't see the whole thing, but if I zoomed out, you can see the pattern, right? I'm just going to be filling in points at all of the integers on the y-axis, right? So what is my range then? How would I write the range? How could I say that? There's a number of ways I could say that. What's one way I could say all of the y values on this function, or the range, which we've graphed in purple, is what? Type it in chat, somebody. What's one way I maybe could say that? The orange one was all real numbers. Every decimal and square root, every possible number was included in the domain. Okay, so whole numbers, but it's not just whole numbers, right? Whole numbers are only 0 and positive, right? How do we say positive and negative whole numbers? What's that set called? Integers. There we go. Yeah, all integers. There we go. So that's one way I could say it. If I wanted to write it as a set, I could even do something like this. What does the ... mean? It's called an ellipsis. What does that mean on the left and the right? What's that ... mean? What do you think? Madeline, what do you think that means when I put that ... there at the beginning and the end of that?
It can go on forever each way.
Yeah, just same pattern forever, right? Good. So integers is really important. You guys don't have the option not to remember integers. Going back to those sets from the start of the year. Integers we're going to use a lot from now on. So remember, integers are just all of the hash marks on a number line, all the positive and negative whole numbers, right? No fractions, no decimals, just the whole numbers on the left and the right of 0 on a number line, including 0, okay? 0 is a whole number, okay? All right, so now last issue then is how do we graph this on a TI-84? And then I'll get you out of here. So what about Desmos? Forgot about Desmos. Couldn't be easier on Desmos. Okay, on Desmos, I would just do f of x equals, and then Instead of a greatest integer function, remember on Desmos, we just call it a floor function. You could, if you want to, you could go down to the menu and let's see, it'd be under functions. And if I go, I think it's under miscellaneous. And there's a floor function, right? So I could do it that way if I want to use that virtual keyboard down there, but it's easier just to type floor, and then open a set of parentheses. So floor of 1/2 x plus 4, and look, it graphs it for me. Okay, how about that? If I want to get all the endpoints in there, I'm going to show you a great trick. This is kind of optional, but this is a great little trick to do this. If I want to add all of those endpoints at once, I'm going to go down here and I'm going to write the same function down with y instead of f of x. So y equals my floor function that I just did. Okay. Only I don't want to graph the whole function. I want to make a table out of it. So if I go up and hit the gear for the edit list, I have the option down here of converting it to a table. So let's do that. If I convert it to a table, now it's only going to be inputting the values of x from the table. Okay, so you know what? I think I could have even done that. Well, never mind. So I'm going to go back to fill in on my graph here. I want to go back to like -10 is the furthest endpoint to the left. So I'm going to make that a -10. Then it looks like every 2, I've got another endpoint, right? So I'm going to hit enter and I'm going to add a -8. And now it picks up the pattern. And so it'll just fill in all those blanks if I keep going, right? And look what happens. I end up getting this entire function. I tell you what, I didn't even have to, I just figured something out here. I didn't even have to redo that function. I could have just done this. I could have just gone up to this guy right here and hit the gear, converted it to a table, and done the same thing. And then just keep going. And look what it does. It fills in all the endpoints for me then. That tells me that the solid endpoints fall on the left edge of each step, right? When I calculated all of those ordered pairs for all of those values of x really quickly, it filled those in. Do you have to know how to do that? No, not really. I mean, but it's, if you want to put the endpoints on there, that's a tricky way to do it. Okay. I'll take a picture of that for your notes. How about? Kind of proud of that one. I just figured that one out today. Okay, and then on the TI-84, here's how you do it. It's the same on all of them, so that's the good news. We only have to do it once. No matter what model you got, it's always the same on this one. So you just go y equals, and then you go to the math menu, the math screen, and then you just scoot over to the number menu. So hit the right arrow, and then there it is right there. INT stands for greatest integer. So I just go down to, I hit 5, and then whatever is inside the greatest integer function, I put inside parentheses. So I'm just going to make that a decimal instead of a fraction, 0.5x plus 4. Close the parentheses, hit zoom 6, and there it is. Okay, and we could use that trick with the trace if we want to figure out where the endpoints are, right? I could just go trace to, and it tells me that, look, there's the endpoint on the left edge of that stair, okay? It's a lot of information, a lot of technology stuff, but you get the hang of that? Does that make sense? Okay, give me 1 to 5 on that. Especially Desmos, on how to do that on Desmos. Okay, not bad. If you're not getting it 100%, go back and look at the videos. Oh, I'll show you something else that I've done that's really, you're going to like this. So if you go to classwork and you go down to instructional videos, notice I've got a YouTube link on there. Okay, so you can go to this, just like before, you can go into the folders and look at the videos, but now I've been uploading these and putting them into playlists on YouTube. So if I click this, it's going to take you to the Unit 3 playlist. Okay, and I'm able to, so here's all the videos that have been uploaded. On YouTube, it's just a lot easier. It's better quality. You can scrub through the video faster by dragging the little, that little, whatever it's called, the thing that tells you where you are in the video, that little circle. You can drag it to the left or the right, and it really quickly will respond. And you can kind of see as you drag it through, you can see little thumbnails pop up, so you can kind of drag it along until you find an example you want to look at. I feel like that's going to work a lot better for you. Okay, that's available.